In the video today, we're going to talk about transition metals in an ionic compound. If you have transition metals in an ionic compound, we actually use Roman numerals to tell the charge of how many electrons those individuals lost. So on the periodic table, group 1 and 2 and 13 and all the way across down here down to group 17, we can actually predict how many electrons we're going to gain or lose all the time. Now if you're in the middle through here, these are the transition metals. For your transition metals, you're going to use Roman numerals. And your Roman numerals are going to tell how many electrons are lost in the process of forming a compound. So with your Roman numerals, that's where you have like 1 or 2 or 3, and you can go all the way up to 10 or so. Usually we just use 1, 2, 3, 4, 5, 6, 7 sometimes for your ionic compounds. Now for my classes, we also learn that tin and lead down here are also going to use Roman numerals because we treat them just like transition metals because they can actually have a 2 or a 4 charge. So with your Roman numerals, you're going to see them in your compounds. And when we talked about naming your cations, we already know that copper here, if it has a 2 after it, that means that you have copper with a +2 charge. So it's nothing different than we did before. However, you're just going to see them with an anion as well. So copper's symbol is Cu. Copper here has a +2 charge. That's what that tells me. Iodine lives in group number 17. Group 17 right here all have a -1 charge. So we're going to pair that up with I -1. Once you have your cation and your anion's charges, what you're going to do is you're going to take away the positive and the negative, and you're going to swap and drop again. So the 2 travels over here, the 1 you don't need to worry about traveling, so you end up with CuI2 for copper 2 iodide. Now if we do another one, I have tin 4 chloride. For my 4 here, I'm treating tin like a transition metal, so that tells me the charge of my tin. Tin is Sn, it has a +4 charge. Chloride is chlorine. Chlorine lives down here in group number 17, it has a -1 charge. Once I have my cation and my anion, then I'm going to swap and drop. So my plus and my minus disappear, this 4 travels over here, and you end up with SnCl4. Now in my next example, I have a polyatomic ion. My polyatomic ion here is sulfate, Ate. So that tells me that it's not sulfide, but one of my polyatomics. So I'm first going to deal with my iron. Iron is Fe. This 3 tells me that iron has a +3 charge. Sulfate, when we look it up, or we just know, is SO4, -2. When I go to swap and drop here, my plus and my minus are going to disappear. This 3 is going to travel over here, so that means that we're going to have to put sulfate in parentheses because we're going to have a 3 out back. And then the 2 goes over here, so we end up with Fe2, open parentheses, SO4, 3. Now on the last one, I have another polyatomic ion. This one is paired up with gold. Gold's a transition metal, and it's telling me that gold has a +1 charge. Phosphate, Ate, tells me it's a polyatomic ion, so it's PO4, -3. Once I have my cation and my anion, the plus and the minus are going to disappear. This 3 travels over here to my gold. The 1 would go to my phosphate. So you end up with Au3, PO4. You can put your phosphate in parentheses if you really want to, but it's not necessary because there's only one of them. So when you have the name and you're writing the formula, those are pretty straightforward. When you have the formula and you need to figure out the charge of your metal, it takes a little bit more work. So Cr is chromium. For my chromium here, this is a transition metal, it's right here. So I need to use Roman numerals to tell the charge of the chromium that was used to swap and drop with my chlorine, which chlorine becomes chloride as an anion. So I'm going to fill in what is the charge that was used to swap and drop. Now, there's a couple ways that you can do this, but the surefire method on always getting the correct answer is to think about it this way. I have 1 chromium and I have 3 chlorines. I don't know the positive charge of my chromium, but I can look up the charge of each of my chlorines. Each chlorine has a -1 charge. So that means total on this side for my anions, I have a -3 charge. If I have a total of a -3 charge on this side, that means that my chromium had to be +3, so they equal 0. So this 3 is going to determine that I have chromium 3 chloride. Now if we do another one, this one has lead. Lead we treat like a transition metal, so it gets Roman numerals. So I put my lead in my middle. I'm going to leave room for my Roman numerals. And then O is oxygen, which becomes oxide. So to figure out what goes in my Roman numerals right here, I'm going to write it out again. I have lead and I have oxygen. I know lead has a 2, oh, you don't know that it has a 2 charge yet, sorry. You know that it has a positive charge. Oxygen you can look up on the periodic table. Oxygen here is -2. So if oxygen has a -2 charge on this side, in order to equal 0, I kind of gave it away earlier, this has to be a +2, so that way they cancel one another out. So that means that I have lead 2 oxide for an answer. Now the next one that I have has a polyatomic ion in it, but it works the same way. Here I have MO, which is molybdenum. Molybdenum is a transition metal. So we're going to write out molybdenum. It is a transition metal, so we're going to use Roman numerals. And then SO4 is sulfate. I'm going to write out sulfate. Now I have 1 molybdenum. I have 1 sulfate. I already know the charge of sulfate as -2. So if sulfate has a -2 charge, molybdenum has to be +2 to equal 0. So that means that I have molybdenum 2 sulfate. Now this last one, I have iron. Iron is a transition metal, so we're going to give Roman numerals. And then C2H3O2, all of that is acetate. So I need to figure out what goes in my Roman numerals. When I figure out what goes in my Roman numerals, I have 1 iron, and then I have 2 acetates. Each acetate has a -1 charge. So that means total with my anions, I have a -2 charge total. If I have a -2 charge total on this side, this one has to be +2 to equal 0. So that means that I have iron 2 acetate. Now if you notice on the last few that I did, or 2 of them that I did, you could actually go through and reverse swap and drop. It doesn't always work. You have to check yourself to make sure. But on this one we had chromium 3 chloride. If we bring this 3 back over here to your chromium, that's where we get the 3 from, because the 1 here goes back to your chlorine to be -1. If you do this method, you always have to check to make sure, does chlorine on the periodic table actually have a -1 charge, which we already knew that it does. So that would give this +3. If you try to reverse swap and drop here, the 2 comes back over here to your iron to be +2. The 1 that's here would come back over here to your acetate to be -1. Acetate does have a -1 charge, so the reverse swap and drop worked on that one. However, we have something like this. Reverse swap and drop does not work on this problem because we have a 1 and a 1. This one would come over here to be -1. This one would come over here to be +1. Oxygen on the periodic table is not -1, it's -2. So that means that you'd have to write this out the long way with O -2, and then lead would be +2 to equal 0. So if you choose to reverse swap and drop, check the periodic table to make sure that it actually worked. If not, you're going to have to write it out like this. The same thing happened with my molybdenum and my sulfate. Sulfate, there's only 1 of them, So that brings us back over here to be +1. There's 1 molybdenum to make it -1. Now sulfate is not -1, it's actually -2. So we would have to write it out the long way, that SO4 -2 and then molybdenum +1. So I just wanted to give that little bit of a disclaimer that yes, you usually can reverse swap and drop, but always double check to make sure that you're doing it correctly.